will be presenting my Physics 2 lab about motion of a falling object with gravitational and drag forces. Here is a quick overview that I will be going over today. First, I will go over Newton's second law and how it relates to the lab. Next, I will be showing you some of my observed data in a tracker video. Third, I'll be showing you my computational model with my GlowScript code. And lastly, I will be making conclusions and assumptions and discuss why my results were not as expected. In this lab, we will explore the change in velocity as a result of a non-constant velocity. Both weight and drag force will be acting on this system. When an object falls to the ground, it has a non-constant velocity, and this is indicated by a F net that is not equal to 0. Here are the velocity and position update formulas. This is a non-constant velocity and it will affect momentum as well. So here is my tracker demonstration to show you my observed experiment. I used a dry erase marker, and so let me bring it back to the beginning. First, I want to show my axes that I did and that I used myself to measure comparison and converted that to SI units. And so now we'll hit play and watch it drop and record the positions. And so as you can see, I recorded the bounce up, which I definitely should not have. So if I would redo this lab, I would have stopped it and ended my time at 0.833 instead of ending at 1.2. And so that's why my data looks a little different than I would have expected. But here, the first code we're going to look at will be our model from our observed data, where we will use weight force as the only force acting on the object. This is also known as gravitational force, and this is calculated on Earth by multiplying the g constant by mass. And so we can scroll through the code and see that I calculated the mass of the eraser and converted it to SI units, and these are the initial positions. These are the delta times. Here is the constant g that we talked about earlier. I set the 1.2 as the seconds ending, and so you'll see in the end that ended up affecting my data very poorly because I should have used the 0.833 like I said in the last video, and equal to the weight because that's the only force acting on it. And here is the weight formula that we did. So as you can see, the force pointing down is the gravitational force, and it takes a second to get down there. But as that keeps going, we'll look at the position versus time and the time versus velocity, and those are very similar to the predicted in our observed data that we just did in tracker. And so now as it approaches 1.2, the final time, it's really small because of the time frame issue, but here is our final gravitational pull. And so now we are going to look at the gravitational force and drag force acting on an object. So drag force is the opposite force to any object in motion, and so since the gravitational force is going down, the drag force should be going up. And so we have this representation of the constant b that is used in our drag force formula. And so here is our change in formula, so this accounts for drag. And so for net force, it is now the drag plus the gravitational force. And so here again is our updated velocity and position. So we'll run this code. So while that loads, it's still very similar trajectory as our observed and our last graph, and same with velocity versus time. Still loading, but gravitational force is the orange, as we would expect it would be, down, and the drag force is represented by this little red arrow because it's so small. I took a picture zoomed in, but it is accounted for in the picture. So now looking at the data, this is the observed data, the gravitational, and the drag. So the drag and gravitational were very similar and look very similar to the model, but the reason that this observed line is so high is because I did not do it for 1.2 seconds. It should have been just at 0.8, which is why this looks the way it does. The way I would have expected my graph to look like if it was done correctly, with the observed in blue, the predicted in yellow, and the orange for predicted motion with drag. And so this is more closely accurate to what it would have looked like, but because of my misrepresentation of time, my graphs did not look the same. Okay, so for conclusions, the terminal velocity is reached when drag force is equal to the force of gravity, and this means the net force is 0 and the object will have a constant velocity. The computational model, including drag force, closely predicts this, but it can't do it perfectly. There is no factor for if it was intentionally thrown down or other things acting on it. So what if? If the object was thrown down, the terminal velocity would remain the same. However, the object would have to decelerate to reach terminal velocity instead of accelerating. So that concludes my presentation.